Perpendicular and angle bisectors. What is a perpendicular bisector? A segment, ray, line, or plane that is perpendicular to a segment at its midpoint. What does it mean to be equidistant? A point is equidistant from two objects if it is the same distance from the objects. So, perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. If it looks like this, if line PM is perpendicular to line AB, and MA is equal to NB right here, look at this picture, then if I draw a line, if I connect A and P, and then P and B, you see a triangle, that means this right here and this right here will be congruent. So if a point on a perpendicular bisector of a segment, this point P is equally distant, same distance from A and B. So equidistance mean is P is equidistant from A and B. They're equally distant is equal. Okay, so if this measurement is 5, that's going to be 5. If AP is 5, PB is 5. So P is the equidistant. So the perpendicular bisector theorem is if a point is on the perpendicular bisector, right here, P, right here, this is the perpendicular bisector. Because this P, this line is bisecting AB and making a perpendicular 90 degree. Then this P, the point, is called equidistant. It is equidistant from A, endpoint A, endpoint B. That's what this means. So what have we already learned that support this? So we can actually write Pythagorean theorem, right? A squared equals B plus B squared equals C squared, right? When you add these two, you get this. That's equal to each other. Then if you do A squared, B squared, they're sharing the same thing. Because this side and this side is same, right? You see this line? Because bisecting means equal. If this is AM, this is 10, that's going to be 10. And this is reflexive, they share the same thing. So this side and this side will be the same if you use Pythagorean theorem. So what have we already learned that support this? Pythagorean theorem. You can write Pythagorean theorem here. So the point is, literally, the P is equidistant. It's equidistant means equal distance, same distance. If it bisects this AB and make a perpendicular line, and then it's equidistant. This is equidistant from A and B. That's the point. That's the perpendicular bisector theorem. Okay? Moving on. Converse of the perpendicular bisector theorem. If a point is distant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So please write this and let me explain what this means. So if PA right here is equal to PB right here, you see the symbols, that means equal, the marking, then PM is perpendicular to AB. That means MA right here is equal to NB. So if I draw a line through this equidistant point, this is equidistant from A and B, and if this is equal to each other, then if I draw a line, you get perpendicular lines. So if at any point PA and PB, isosceles triangle or equilateral triangle, have PA and PB congruent, equal, that means if I draw a perpendicular line, it's going to be 90. And then this side on the bottom, MA and MB, they are also equal. So if a point is equidistant from the endpoints of a segment right here, same same distance, let's say it's 10 and 10, then it is on the perpendicular bisector of a segment. That means this point is on the perpendicular bisector. Right here, this line is called perpendicular bisector. This line is perpendicular bisector. So if you have an equidistant point from A and B, then this point is on the perpendicular bisector. That's the conclusion that we can make. Okay? That's called converse of the perpendicular bisector theorem. Please pause and understand, and you can write this down. If you are confused, you can ask me during class. So basically, if P is equidistant from A and B, you can have perpendicular lines with 90 degrees, and this bottom two will be equal to each other. That is converse of the perpendicular bisector theorem. And this line, this red line, is the perpendicular bisector line. And this P is equidistant from A and B. Okay? Alright, so let's look at the example here. In the diagram shown right here, PQ, line PQ, is perpendicular bisector of CD. What segment lengths in the diagrams are equal? So look here. This P is equidistant from C and D. So the CP is equal to DP. They are equal to each other. So make a mark on your picture. So because of perpendicular bisector theorem, which is the lesson today. So please write CP is equal to DP because of perpendicular bisector theorem. Please write that on your notes. Explain why T is on PQ. So T is not on the diagram, it is not on PQ, but if I extend a line goes forever, right? P will be eventually on this line PQ. See this line? Keep going. So explain why T is on PQ, because you see this 7 and 7. 7 and 7, this TC is equal to TD, right? If they're equal to each other, then this is called converse. You're looking at the sides and going backwards. That's what we call this bisector theorem converse. Instead of looking at the perpendicular bisector and determining this side and this side is equal, if you already have equal side, then you go backwards. You converse and say, oh, TC is equal to TD by using the converse. So when do we use converse? When they already give you the left side and the right side, they are equal to each other, then you use the converse theorem to prove that T is equidistant from C and D. So converse, you go backwards. The first one, you look at the line and then determine these two are equal. Converse, you look at the sides and determine if T is the equidistance from C and D. So they're like the opposite way. So that's where the converse theorem comes, which is what we have here. The converse, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So we can actually use the converse way. If they give you the sides and show them they're equal to each other, prove that T is the equidistance from C and D. And this is perpendicular to each other, okay? Because equidistance is on a perpendicular bisector. T is perpendicular bisector on perpendicular bisector of P and Q. P and Q is the perpendicular bisector because this is going to continue because it's a line because of this arrow, okay? At any point, if you are not sure, just ask me during question. All right, so we're going to look at this right here. So solve for M N right here. So the bisector, perpendicular bisector theorem is the lesson for today. So right here you have bisecting, this is the M and O, this is a perpendicular bisector of N and P. And then M is the equidistant, is this M, point M is equidistant from M and P because you have the perpendicular lines. It only works for perpendicular lines or if the left side and the right side is equal to each other. So how do you solve for Mn, the length? So 6x minus 1, 3x plus 8, they are equal to each other because of perpendicular bisector theorem, right? So you make it equal to each other and you solve for x. So you do minus 3x, add 1, and then 9 divided by 3 is 3. So x equals 3. Once you find x, that's not the answer. We need to find the measurement of mn, the distance. So you plug in 3 into 6, which is 18, minus 1 is 17. So if this is 17, guys, then this is 17. Because 3 by 3 is 9, plus 8 is also 17. So it only happens when you have Pythagorean theorem, when you have perpendicular, bisector, equidistant, the left side, right side is equal to each other. This whole big triangle is equilateral, isosceles triangle. Isosceles, okay? Alright, so let's look at this. Definition of distance from a point on a line. So this is a different one now. So please write the distance from a point to a line is the length of the perpendicular segment from the point to the line. When a point is the same distance from one line as it is from another line, then the point is equidistant from the two lines or rays or segments. So everybody copy this, and I can actually explain using an example. So angle bisector theorem. Let's write this first. If a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. So right here you have QS bisects angle PQR. Okay, that's given. And then PSP right here is perpendicular to QP. You can see this little 90 mark. So this small line right here, SP, is perpendicular to that. And then SR is perpendicular to this QR. You can see that right here, 90 here, 90 here. So this line is perpendicular, this and this is perpendicular. If that happens, then SP, this right here, SP and SR, they are equal to each other. That's angle bisector theorem. Okay? So if you have a diagram like this, if PQ is bisecting this angle, that means this small angle is cut it in exactly half. Same measurement. Okay? And if this line is perpendicular to this, if this line is perpendicular to that, I'm going to give you that, then you can conclude that the measurement of this and this is same. Let's say if this is 5 centimeter, then this is 5 centimeter. So that's called angle bisector theorem. So we're going to, your favorite proof, right? Just kidding. We're going to use that angle bisector theorem to prove, okay? So given is R is on the bisector of QPS, okay? So this R is on the bisector of, this is the bisector right here, PR, of angle QPS. So we're going to prove that RP, right here, RQ, I mean this is congruent to RS. So what we're going to do is write the given. You're going to write down that this angle right here, SPR and QPR is congruent because of definition of angle bisector. And you're going to say this angle Q and S are right angles, and all right angles are congruent. You're going to write that. And then you're going to say PR is equal to PR, which is reflexive property. They share this. And then you can say that this triangle is congruent to this triangle because of angle, side. Angle, side. That means this side is congruent to this side because it's CP, CTC. So when we're proving this, we're using triangle tools and CP, CTC to prove these two, this QR and SR are congruent. Please pause the video and copy this. Next thing we're going to look at is converse of the angle bisector theorem. If a point is in the interior of an angle and is equidistant from the sides of the angle, then it lies on the bisector of the angle. So basically when you see converse, they're giving you these two are equal to each other and saying when that happens, you have a QS bisects this angle. That's what it means. So they're giving you the sides, and you can conclude that QS is bisecting this angle PQR. So you're going backward, just like the other.